The general definition for a redox reaction is a reaction in which electrons are transferred. They are transferred from one to the other. Okay, that's the basic form, bless you, of an oxidation-reduction reaction. When we see a transfer of electrons, it generally means that we're dealing with ionic compounds, because ionic compounds and ionic bonds are talking about transferring electrons. Covalent bonds are when they share electrons, and so ionic bonds are a trading of electrons. And so when we see redox reactions, most of the time, not all the time, most of the time we see it occur with ionic compounds, okay? And we'll see them change kind of charges or states from one side of the equation to the other. And so that's what a redox reaction looks like. Your book walks you through one on page 170. I don't want to look into that too much, but what it talks about is when we have sodium atoms plus chlorine atoms, it yields sodium chloride. Okay, and so you see in the first part, the first picture, we have pure sodium metal. Okay, and it takes 2 sodium atoms paired with 1 chloride gas molecule to form salt, sodium chloride. And so we are going to look at this, what we call a change in oxidation state from the time when they're by themselves, from when they come together. There's this transfer of electrons or trade of electrons. So we're going to look at what that means in just a little bit, okay? Before we can get into the actual reaction part, we have to identify what we call an oxidation state or an oxidation number. And so let me tell you just a second about what an oxidation number is, and then I will give you plenty of time to write down these rules, okay? And we're going to talk through them a little bit, but let me tell you what an oxidation number is. An oxidation number is kind of a pseudo charge. It's not really a charge, it's not a true charge, but it's kind of a charge. Oxidation numbers give us a way to identify where electrons are distributed within a molecule. Okay, it tells us where electrons are distributed within a molecule. So we'll see oxidation states change as we go from a reactant to a product, because in the product state, the molecule is reconfigured, right? It's something new. And so the electrons might be distributed differently from when it's a reactant to when it's a product. So we're going to look at these oxidation states, and then we'll be able to tell what happens from the time it goes from, let's say, silver chloride and combines with sodium nitrate. Now it's silver nitrate. That's a totally new compound. So silver might be configured differently when it's a reactant than when it's a product. Okay, does that kind of make sense? Oxidation numbers give us this kind of pseudo charge. And so we need to write down these rules for oxidation numbers, remembering that they kind of go in order. Okay, they have to go in a certain order. And here, really what I want you to do is I want you to move up number 5 right before oxygen. I want fluorine to go first. Okay, we have big 3 elements here, fluorine, hydrogen, and oxygen, and I want fluorine to come first. Okay, so I'm going to give you 5-6 minutes to write down all these rules, and then I'll talk to you through how they apply to this. I flipped those for you, but I want to add one rule to this. Okay, if none of our big 3 elements are present, fluorine, oxygen, or hydrogen. So if fluorine, oxygen, hydrogen aren't present, the most electronegative atom gets to keep its regular charge. Okay, if our big 3 are not present, the most electronegative atom gets to keep its charge. So when we say most electronegative atom, do we remember the trend for electronegativity? We haven't talked a whole lot about it, but essentially it means closest to fluorine. Fluorine is the most electronegative atom we have. it wants electrons more than anyone else because it's got 7 valence electrons in its first shell. So it wants to complete that shell badly. It will take electrons from anyone and everyone. Makes it the most electronegative. So that means elements close to fluorine, they're more electronegative than ones far away from fluorine, right? That's the trend that we see on the periodic table. So if you're unsure which one gets to keep its regular charge as its oxidation state, it's the one closest to fluorine. Okay, and I know these rules seem really abstract right now because we haven't even put an example in yet. But they will come together as we do problems. Okay, I promise. These oxidation numbers we used mostly for covalent compounds. I know I told you redox reactions are mostly with ionic, but we assign oxidation states mostly for covalent compounds because ionic compounds get to keep their regular charge usually. Okay? So again, I know this is abstract and a little arbitrary right now, but we'll put it together. Okay? So let's find the oxidation states. I want to do, first one I want to do is, actually I don't want to do any of these yet. I want to try some on our own first. Okay. Oh my. Okay. I want to do PF3. Okay, we're going to assign oxidation states for this compound, PF3. Okay, and so when I assign an oxidation number, I'm looking at an oxidation number per each individual fluorine atom. Okay, each individual fluorine atom. And each individual fluorine atom, we know, based on our rules, has what oxidation number? 0. Not 0. -1. I put oxidation numbers on the top, right? Assign oxidation numbers on the top. Not to the side like a charge, because it's not really a charge, it's kind of a charge, okay? In this molecule, what it's saying is that if we have P bonded with fluorines, 3 of them, each of these fluorines is going to pull the electrons in this bond closer to itself. So fluorine has now an extra electron surrounding it, right? It wants electrons so badly from this bond, it's pulling it closer to itself. So it's taking on this kind of -1. So each fluorine has a -1. Okay? And so if we have 3 of these, that gives us a total charge, not really charge, but total of -3, right? -1 per 3 fluorine molecules gives us a total of -3, right? Look at your, second to last rule. What should our charges add up to? What should our oxidation numbers add up to? The charge of the ion or the charge of the molecule. So originally when I wrote PF3, does it have any charge listed? No. So we want the totals at the bottom to add up to 0. The totals, not each individual oxidation number, but the totals. Okay? So I know fluorine each has a -1. That gives me a total of -3. What value needs to go here to make this equal 0? A +3, right? This value needs to be a +3. And how many phosphorus atoms have to split that +3 charge between them? 1. There's just one phosphorus atom, right? There's a 1 there since there's no subscript. So that means phosphorus has an oxidation number of +3. Okay, so our final answers here are -1 and +3. Our totals just get us to our final answer. They're not part of the answer, right? Our oxidation number for fluorine is -1 and for phosphorus is +3. Okay, these totals just allow us to get to that point. Okay. So we followed the fluorine rule and the total sum rule there, right? They go in order. So fluorine has to come first, then we look at our sum. Questions? I know it seems a little bit arbitrary for right now, but we're going to use this, okay? Let's try another one. Can you name it first? Good. Sulfuric acid. Good. Okay. So, does it have one of our big 3 elements? It has hydrogen and it has oxygen. So I like to go in order. Okay. Oxygen is, we know, a -2. And how many oxygens do we have? 4, which gives us a total of -8. Total of -8. So, what do we want our totals to add up to here? 0, right? Because our overall acid had no charge, right? We want it to add up to 0. So now we've got 2 variables that we're missing, right? But we've got one of our other big 3 elements, so we jump to that. Okay, what do we know about hydrogen's oxidation state? +1, and there are 2 of them, so that gives me a +2. What x value has to go here to make this equal to 0? +2 plus x minus 8, what number gives us? This has to be a 6. Okay, it has to be a +6. Not just 6, right? If it's a positive, you got to put that plus sign in there. Okay, so +6, how many sulfurs have to split that? Just 1, right? There's only 1 sulfur atom that takes that whole +6 charge, right? So the way you tell our answer is hydrogen equals +1, sulfur equals +6, oxygen equals -2. Okay, is that making a little bit more sense?
So it's just basically a math problem.
Yeah. And it almost always works in this square, right? We multiply down, we add over, we divide up, okay? Almost always you're going to work outside in. So the last element that you adjust is going to be that guy in the middle, if you have 3 like that. If this one is a metal, it gets to keep its regular charge. We'll see that here in a second, okay? Yeah?
How do you know if it's supposed to be equal to 0 or equal to -1?
Okay, so we're going to do one that looks like that. But since we wrote since we wrote sulfuric acid, H2SO4, this molecule has no charge. So that tells us that it has to equal 0. If it would be -2, then this would equal -2. Okay, so we're going to try one of those now. Okay, let's do carbonate. CO3 -2. So now the total oxidation numbers have to add up to -2. Not to 0, to -2, because our molecule or our ion has a charge. Okay, so what do we know about oxygen? -2, and there's 3 of them, so that's a -6. We want it to be equal to -2 since that's the charge on our ion. So what value goes here that gets us to -2? +4. And how many carbon atoms do I have splitting that? Just 1. So that means carbon is a +4 and oxygen is a -2. So the reason we do this is that we're going to see maybe carbonate combines with something else and forms calcium carbonate. So in the second, as a product, calcium carbonate might distribute electrons differently than just carbonate. So we're going to be able to determine what type of reaction that is based on these oxidation numbers. So these help us with our oxidation or our redox reactions. Okay, let's try some of these now. Okay, we already did carbonates. We don't have to do that one. K2Cr2O7. Okay, let's try that one. I'll rewrite it a little bit bigger over here. K2Cr2O7. What do we want our totals to add up to in this case? 0, right? Because our molecule has no charge. All right, so we know oxygen is always a -2 times 7 gives me -14. We already said we wanted to add up to 0. Now we go outside in. So we move over here. Since potassium is a metal, it gets to keep its regular charge as its oxidation state. Since it's a metal, it gets to keep it. So if you want to write that into your rules also, that might be good. But metals, 99% of the time, keep their oxidation state unless they're in the middle. Okay, so there's not really a written rule that puts that into words very clearly, but you're going to work outside in. So this is the one that usually gets adjusted. Okay, but since potassium is our outside and it's our metal, right? I know chromium is a metal too, but it gets adjusted last. So that's a +1 because that's potassium's normal charge. And there's 2 of them. That gives us a +2. So what value fits in that x to make it equal to 0? +12, right? 2 + 12 is +14. -14 is 0. So now with chromium, it's got 2 atoms to split the +12 between, which means each of them have a +6. right? It has a +6 oxidation number. So if you look at chromium, that's really not one of its charges, right? +2 or +3 is its charges. So when it forms in this molecule, it takes on a little uncomfortable state, right? It takes on a little bit different oxidation state. Questions about that one? Okay. We already did carbonate. Let's do MnO2. MnO2. We know oxygen's -2, which gives us -4. Is that what you had? Right? You build the box. So you start here, build the box. Multiply, add or subtract, divide up. Okay? Why don't you do the last two on your own? That's PCl5 and SF4. PCl5 and SF4. Do those two on your own. Okay. Ethan, can you tell me what our oxidation states were on the first one?
I got ES5 and chlorine is -1.
Do we agree? Yeah. It is important that when you have a positive, you do put that plus sign. So if don't just put 5, we got to put +5, so you make a distinction between positive and negative. Don't just make me think you forgot it. Okay? Second one. Trey, what'd you have on the second one?
I got S is +4 and F is -1.
Perfect. Okay? Questions with any of those? Okay. All right, now we're going to look at how this applies to reactions, okay? We already said in redox reactions there is a transfer of electrons. There is a transfer of electrons, okay? And so these transfers may form ions or they may form new compounds, right? It could be either one. These are the two possibilities that could happen. We could have an oxidation or we could have a reduction happen. Okay, so write down what you need here and then we'll look, I'll talk through it just a little bit more. Going to be really helpful. Oil rig. That means oxidation is loss. Reduction is gain. That's going to be something that you're going to want to remember. Oil rig. Oxidation is loss. Reduction is gain. And we're talking about electrons. Okay, if you lose an electron, that means your charge or your oxidation state goes more positive. Right? It becomes more positive. Does that make sense? If you lose electrons, that means it becomes more positive. If you reduce or you gain electrons, that means your oxidation state becomes more negative. And so as we're looking at these reactions, we're going to want to be able to tell which element is oxidized, which means it's lost electrons, and which element has gained electrons, which means it's been reduced. Okay, we're basically going to have a switch of each. One of each. So you need to remember the acronym oil rig. Write it down, highlight it, whatever, remember it. Oxidation is loss, reduction is gain. Okay, are we ready to look at some reactions? Okay, write down these two terms for agents, oxidizing agent or reducing agent. This is telling us which one kind of put the reaction into motion or which one did the accepting or the donating. Let's look just at this first reaction here. I'm going to write it a little bit bigger for you, but we're going to look just at this reaction. Is that big enough? Can you see it okay, or do I need to write it bigger? We good? Okay. I'll write it then. So get the reaction written down, and then we'll look through oxidizing and reducing. When we're looking to determine if there's been an oxidation-reduction reaction, the first thing we have to do is find our oxidation states for each element. Okay? So we're going to do that first. We're going to go through and find our oxidation numbers for each element. So what do we know about the oxidation number of an atom that's by itself, or a purely elemental compound? It's 0, right? So that's true for zinc and for what on the other side? Both of those have oxidation states of 0. And that's true because if an atom is by itself, there's no uneven distribution of electrons, right? It's just around that atom, okay? All right, HCl, okay? Oxidation numbers for HCl. What do you think hydrogen's is going to be? +1, and that makes chlorines -1, right? On the same page with that? Now let's move over to ZnCl2. Does it have one of our big 3 elements? No. So chlorine keeps its regular charge as its oxidation state, so -1. And that gives me a -2, which I want to add up to 0, right? And so that means zinc has to be +2. Okay? So we need to look. Is there a change in oxidation states from the left side to the right side of any of our elements?
Yes.
Yes. Which are the elements that changed? Zinc went from 0 to +2. And hydrogen went from +1 to 0. Does that make sense? There's been a change in 2 of them. Chlorine stayed the same. It was not oxidized or reduced. So if we look at zinc, zinc went from a 0 to a +2. So did it gain electrons or lose electrons? It lost electrons. It went from 0 to +2 charge, which means it's down 2 electrons. So that means it lost electrons, which means it was oxidized or reduced. Oxidation is loss. Reduction is gain. That's where that oil rig comes into play. So this lost electrons, which means it was oxidized, right? This was what was oxidized. Now if we look at hydrogen, hydrogen went from +1 to 0. So what happened? Did it lose electrons or gain electrons? It gained. So that means it gained electrons. So what does that mean that it was? It was reduced, right? Oxidation is loss, reduction is gained, right? That means of electrons. So if this was oxidized, then that means that it was the electron donor, which means it was the reducing agent, right? So zinc was the reducing agent because it donated 2 electrons. Does that part make sense? It donated 2 electrons. Hydrogen gained electrons, which means it was the oxidizing agent. Okay? How do we feel about that?
So the one that's oxidized is the
Reducing agent. Exactly. They go in pairs like that. So if it was oxidized, that means it was the reducing agent. And if it was reduced, it was the oxidizing agent. Okay? Does that make sense? Okay. Yeah, Ann.
So for like 2HCl and zinc chloride, like how do I know what they should equal?
So since they didn't start out, like HCl doesn't have a charge, the totals should equal 0. So that's how we got the +1 and the -1, because they're just one of each.
Okay.
Okay, so since there's no charge in the molecule, which was the same for all of those, they should equal 0. If there was an ion there, then it would equal the ion. Okay, yeah.
How come, say, for instance, 2 electrons, but then hydrogen?
Okay, so we would go on to balance the redox reaction, and we would say we need another electron on this side, but we don't have to do that. We're not going to do that in our class. Next year you'll get into that a little bit more, but I'm just introducing redox part of it. Yeah.
For that one, how do you know chlorine gets the negative one?
Okay, so we started with hydrogen. Can I clear this off so I can write it a little bit clearer? Okay, we started with hydrogen because it's one of our big 3. So HCl. Hydrogen's one of our big 3, so it's a +1. And that means that I've got to get something here to equal 0, which means it's a -1. And there's only one chlorine atom, so that's how I got my -1.
I guess I meant in the zinc.
Oh, I'm sorry. Okay, since none of our big 3 are present, the one on the right side of the compound gets to keep its regular charge as its oxidation number, okay, which is also the most electronegative. Okay, we got time for one more, and I know this one is an oxidation reduction, so we're going to do C. If you go through and all the oxidation numbers are the same for both sides, that means it's not a redox reaction, so you wouldn't have to assign oxidation or reduction, and that was what happened in B, but I don't have time to go through that, so we're going to look at this one. So CuCl, none of our big 3 are there, so chlorine is a -1. There's only one chlorine there, and one copper, which means it needs to be +1. Agreed? Okay. That forms CuCl2, so -1, -2, which gives me a +2 now for copper. And elemental copper is what? 0. Okay, so the oxidation states there, do we feel okay about that? Remember, we don't really care about the total. So once you have the top numbers, your oxidation states, you can get rid of the totals. We don't need those. We just need what the actual oxidation numbers are. So the changes here happened in what? Just copper. Copper went from +1 to +2 and 0. Okay? So, we're going to look at this transition first. So, to go from copper to copper chloride, what did we do? To go from +1 to +2, we lost electrons, which means what happened there? Oil rig. Oxidation is lost, so it was oxidized. Okay, and then to go from the elemental, or from here to the elemental, we gained electrons, right? We went from +1 negative, which means it was reduced. Okay, so that was kind of tricky because it's got it in 2 places. So this copper was oxidized, this copper was reduced. Okay, I'm not going to have examples like that where you've got multiple very often, right? Your book gave me this example and I don't really love it. But that's, I think, how you'd write that out. Yeah.
So to find another one like that, we would have to do
Yeah.
copper twice just
Yeah.
so we have the chlorine.
That's right. That would be my understanding. I'm going to do my very best to not give you problems that look like that. Yeah.
So everything that's elemental equals 0.
Yeah. That's number 1. Rule number 1. Anything elemental is 0. Okay?